So already you have noticed some similarities between the multiple regression model and the simple regression model. Simple regression model. Okay. So the only difference so far is that now we have several explanatory variables instead of only one. Okay, so in the multiple regression model, the response variable is still linearly related to the k number of explanatory variables, and we have this equation. Okay, so this is the population error term, okay, which is normally distributed with mean 0 and variance sigma epsilon squared. Okay, and if you plot the y versus all the other explanatory variables, they should be linear, right? And if they are not linear, then you know how to make a transformation and make them linear. Okay. So what's important is that the error term, the population error term, is assumed to be independent, which means that you have no pattern. Okay, no pattern when you regress, or if you plot the error term onto the response variable, then you should see no pattern. Okay, or for time series, you look at the Durbin-Watson, right? So you remember Durbin-Watson. You could check. If there were autocorrelation in the errors with the Durbin-Watson test. Okay, and you assume that the errors have equal variance around the regression line, which means that the dispersion of the errors, they are quite similar no matter what kind of xi you look at, right? And this is y, and the errors should be normally distributed, right? So, and these are just the same error terms or assumptions about the error terms which you found in the simple regression model. So the simple regression model is really just the multiple regression model with only one explanatory variable. Okay, so if we go to our example, then we'll look at what goes into our model. So what we have is that we have data from a sample of 65 stores, and we have one response variable, and that would be sales per square meters, and that would be our y, and that's our response variable, and that's annual sales at a given Starbucks store per square meter of retail space. Okay, and so this is in kroners per square meters, right? And you have two explanatory variables, which is median income, that would be x1, and number of competitors, which is the second explanatory variable. So the median income is the median annual household income in the area measured in thousands of kroners, okay? And the number of competitors is the number of competing stores within half a kilometer, because you tend to not walk more than half a kilometer to get a coffee, right? So let's see. And these data, they usually come in a table where you have sales per square meter, and of course you have the store ID, and then you have for example the median income and the number of competitors. Okay, and for example the first store has sales per square meters of 600,000. Okay, and the median income in the area might be 500,000 kroners per year, and you have two competitors. Okay, so what you do first would be to plot your y, your sales per square meter onto the potential explanatory variables. Okay, so this is the median, so the median income and the number of competitors. Okay, okay, and you see that, well, definitely from the median income you have quite a linear positive slope relationship. So, and that would be logical, because if median income in the area goes up, then sales probably go up because people have more money to spend on coffee or on premium coffee. Whereas here you see the annual sales on the y-axis and the number of competing stores within half a kilometer on the x-axis, and it's basically flat, right? Or maybe negative or slightly positive. So maybe it's not really relevant, but we can get a better guess for these regression lines by regressing a y on each of the x's in turn. Okay, so let's just run a simple regression model, 1x, okay, and what you find when you regress sales on median income, you find that the r squared, is 0.50, which means that the median income explains 50% of the variance of sales, and down here we have our y, that's sales per square meter, and we have our x, that's our median income, and our intercept and our slope. And in this case, we are interested in our slope. So what we do is that we got a slope of 69.56, and what do we make of that? Well, we see here that the t-value, it's 7.96 standard deviations away from 0, and so it's statistically significant. But what is the interpretation? The interpretation is that if median income goes up by 1,000 kroners per year, then the sales per square meter goes up by 69.56 kroners. Okay, that would be per year. Okay, because the sales per square meters, that's also per square meter. That's sales per square meter per year. Okay, so that's a positive relationship, and we saw that here from the data. It was quite easy to see that if a median annual household income in the area goes up, then the sales per square meter go up. Okay. Whereas if we regress sales on number of competitors, we see that firstly the r squared is quite low. It's 0.0044, which means that the number of competitors actually does not explain the variation. Basically, no variation in the sales per square meter per year. Okay, and if we go down here, this is our y, this is our x, and our, no, that's not the intercept. This is the slope, and if we look at the slope, we see that it's positive, but the t-value of 0.53 means that this value is only 0.53 standard errors away from 0. So we can't really tell if this coefficient is positive or negative or 0. And you have here the 95% confidence interval, which, or we should do that, which includes 0 here, right? And so, but if we look at the value, what is the interpretation? It's really if the number of competitors in the area increase by 1, then we expect sales to, okay, sales per per square meter per year to increase by 498.92, okay, or 3. And you might actually stop and think about that. Is it logical that if there's another competitor close by your store, then your sales will increase? Is that logical? And another thing is that this coefficient is not statistically significant. Does that mean that we should not include this variable into our model? We are going to see that multiple regression takes care of the interactions between the explanatory variables, such that we get more insight into this. So that's the next video.